talk is called Reasoning is Overrated. I should immediately put in a disclaimer that says it's overrated in artificial general intelligence. It's very useful in other things. A quick overview of the talk. I should warn you that normally I do very technical talks, and today I have toned it down quite a bit. I'm trying to get the message through, but the message will not be as thoroughly supported as it is on my other talks. If you want more meat on the bones about the things I'm saying, go to my website and look at my other videos. There are about 7 videos of them.
Yes, we can hear you.
Okay, one moment. Let me fix it. One. Hello. One. Is that better?
Yeah.
Okay. So that's the negative of that. I will have to speak now. So, I'm going to be talking about reasoning and understanding most of the time, and I'll get to the summary of consequences early on. You just had a snack and you're going to fall asleep if I wait until the end. So I'm going to give you the punchline there, and then I'm going to do a little bit of filling in of the background, but not too much. And those are the two things I talk about at the end there: problem-solving strategies and reduction tools. So this is Daniel Kahneman, Nobel Prize winner in economics in 2002, and professor emeritus at Princeton. And he wrote this book called Thinking Fast and Slow. And in that book, he basically discusses what a lot of people are calling dual process theory. This theory was basically first discussed by William James in 1890 and by other people over time. The theory basically says that there are two different processes in the brain. Two different kinds of thinking is going on. There's a fast subconscious intuitive understanding, and there is a slow conscious logical reasoning. And they're different. Let's look at some of the features of those, the characteristics. Like I said, understanding is instantaneous. It takes only a few hundred milliseconds to understand, for instance, what I'm saying. Whereas reasoning is a step-by-step process. It takes seconds to years. Einstein famously took decades to figure out general relativity. Understanding is subconscious, and reasoning is conscious. We can introspect our reasoning process and notice when we're working with a math problem, that where did I go wrong? Whereas understanding, we don't have no clue about how we understand the language. Understanding is involuntary and reasoning is voluntary. And this is actually a very nice little division, a nice little difference, because we can conduct a thought experiment and consider that, suppose you wanted to go for a vacation in Europe, and you're planning the trip, which sites you want to see, which towns to go to, how to travel between them, and so on, which hotels to stay in. This process can take a long time, take hours to weeks. But you can stop in the middle, you can plan a couple of steps, and then take a coffee break, and come back to the next day. So reasoning can be stopped and started again, or abandoned if you feel it. But understanding, such as understanding language, or understanding how to walk, understanding how to ride a bicycle, these things, you cannot turn them off. Once you learn to understand English, you cannot turn it off. I like everybody to consider this right now, basically, because I'm going to be assuming for the rest of the talk that dual process theory is correct. And if you all assume the same thing, it makes this easier. So, intelligence as such is splits into reasoning and understanding. Reasoning, as I said, a conscious logic-based deliberation versus a subconscious intuition-based recognition. Recognition of objects, agents, concepts, relations, patterns, abstractions, and semantics. You have to read that. And it's pretty clear that those two understanding is the more fundamental. If you look at the evolutionary record or look at animals, for instance, think about dogs. They understand a lot, but they don't reason. And it's also pretty clear that the understanding is more important than the reasoning. And basically reasoning is overrated. Can we make an estimate of that? Well, if we look at the optical nerve and other basically indicators, we can estimate that the brain takes in about 10 million bits per second. But multiple psychological studies have shown that we are consciously aware of at most about 100 bits per second. Numbers vary from 40 to 140, sticks with me highly up to 140. But on the order of magnitude, these are very rough numbers. 10 million bits to 100 bits per second. So we do the division and we figure out that the brain spends only about 1,000 of 1% on their cycles of reasoning. Most of what we do is subconscious understanding. So reasoning is at best a painted layer on top of understanding. In the 20th century, artificial intelligence research was overly focused on this reasoning part. Now it's time to take a look at the understanding part, and that's what my research into artificial intuition is all about. It's important to note here that reasoning requires understanding. It rests on top of it. When you're reasoning about something, like a logical problem or math or whatever, the variables that you're considering are anchored in your understanding of the world. So understanding comes first, and then reasoning is built on top of that. Okay? So if you're building an AI, you must start with the understanding part. You can't start with logic and reasoning, because that would be like building a castle in the air. You have to have the foundation. So AI research has spent 1 million man-years, that's a conservative estimate, over 60 years' time, on the wrong problem. That's it. If this is true, and I believe it's true, what are the consequences? Let's consider the properties of a possible AGI. I mean, this is an overview. Like I said, details are going to be in the second part of the talk. All intelligent agents are fallible. This is the first, the most important message I have. All intelligences are fallible. There is no perfect intelligence, period. It's theoretically impossible. I'll explain why. So all AIs are best effort only. All intelligence, artificial or human, for instance. We make mistakes and we learn from them. It's very important the AIs we build do likewise. Our AIs must make mistakes and learn from them. We understand what matters. When something happens to us, we basically we know what's important to remember, to learn from. We know what is unimportant and which we can ignore and forget. That's called salience. It's a very big problem. It's very little effort has gone into figuring out salience in the AI community. We do understand and exploit contexts, and so must our AIs. They have to understand large contexts of stuff. Language, for instance, is extremely context sensitive. And the large part of what I'm talking in the second half is talking about models and how we can create models of the world. But the key point, again, I like to emphasize, is it is the AI that has to create the model of the world. You can't have the programmers who make the AI create the model of the world, because the world is very large, it will never be done. So our AI should be based on intuition and not logic, because logic actually doesn't work. Intuition will work, and I'll explain what intuition is to be. So why not logical reasoning? Why is logic and reasoning and models of the world, why are they not the way forward for AGI? Because the world is chaotic, irreducible, it changes over time, emergent effects. All four of those phenomena make model making impossible. You can't make models of the world because, for instance, changes over time. The moment that you made a model, it's immediately obsolete, because behind your back the world has changed. And the predictions you made with your model are going to be incorrect. So So comprehensive models of the world cannot be made. We can make models of small pieces of the world, and basically say, we can deal with this little domain, we can't deal with the whole thing, and then we write code that deals with this little thing. This is code programming. This is not AI. If you want to have something that is worthy of the name AI, it has to understand basically the entire world. And that's expensive, so instead we won't make one that learns as it goes. All reasoning requires models. When you're thinking about something step by step and so on, you're actually not thinking about the world as such. I mean, you're not directly interacting with the world, you're interacting with the model of the world in your mind. So all reasoning requires models. Complete, correct, and unambiguous input is almost never available. There's optical illusions, misinformation, lies, all kinds of stuff, and like I said, there's lots of stuff happens behind your back, out of your view. So you don't have correct input data. Now, logic-based solutions in general, they require correct input data. And logic cannot operate without correct data. So everything we thought we knew about AI may be incorrect, because it's based on the idea that logic is what is at the bottom of intelligence. So, logic, reasoning, reduction knowledge, they can't be used as the basis for AGI. They may be emergent effects at a higher level, but they are not what we should start our implementation with. Infallible, omniscient, superhuman, godlike AGI, that's my favorite phrase, is totally impossible. Recursive self-improvement has hard limits. You've heard of recursive self-improvement as basically the way that AI will take over the world by improving themselves and so on until they are so small that they will take over. Turns out that if all AIs are fallible, then the self-improvement will be fallible. And at some level, the errors accumulate and you basically can't get any further. So I don't believe in recursive self-improvement. And unfriendly AI is another term that a lot of people talk about. Basically AIs that go rogue and want to exterminate all humans. Well, since all intelligences are fallible, we can pull the plug on them. We just wait for them to make a mistake and then we pull them off, pull the plug. And I also believe that the AI singularity is unlikely. Now, I said AI singularity can be many things, but I don't believe we can trust on AI to basically bring us to that point. We will see AIs will be very useful, they will be very different than what we have been thinking about so far. But this goes also down to what we are doing today in the artificial community. The techniques and the methods and the tricks of the trade that we use are also specious. If we want to get to general intelligence, all of these things are basically we may not be able to rely on them because these all assume that intelligence is based on reasoning. So what's the good news? So logic-based AGI research has taken 60 years. But since they've been working on the wrong problem, we can basically ignore how should I put this? Intuition-based AGI is much easier than what we've been trying to do so far. It's not going to take another 60 years to get that right, because we are now addressing the correct problem. In fact, I have been gone on record as saying that what we want to do in an AGI is going to be about 10,000 lines of code, no more. This is, remember that Microsoft Word is 10 billion lines of code, so an AGI can be about 1,000 of the size of Microsoft Word. Available in the next few years. And I hate to call them artificial intelligences because it's tainted by all of these ideas about logic and unfriendly AI. I call my machines understanding machines. They basically mostly try to understand language. That's the main thing that they try to do. but they will understand the language as well as, say, a 14-year-old kid. And all of them, we can understand all the human languages we want. We just pick one and teach it to it. Today we may hear a lot about deep learning. And deep learning is actually one that is on the right path for this kind of AI, of the other kind. Basically, it's symbolic versus sub-symbolic. The old kind was symbolic, and we're now getting into the sub-symbolic stuff. It's been going on for many years, but it's basically coming in on its right now. And artificial intuition, as I said, is my research on it. There's a few others. The greatest surprise to AI researchers is that they need to create computer programs that jump to conclusions on scanned evidence. This is not how we normally write programs. We assume everything is logically correct. So let's look at the characteristics again, different set. So understanding is built using intuition as the algorithm. Intuition is an algorithm when you get into computers. Just like logic is the algorithm of regular programming. Intuition is used in everyday life. Almost everything we do intuitively. We use models and logic mostly in science. It's a very, very tiny fraction of society. Understanding solves trivial problems in complex contexts, such as matters of the tribe and matters of the heart, as I used to say. The complex is very complex. Should I marry that other person or not? There's like a million factors that go into that, but the answer is a yes or no. So it's a trivial problem in some sense, but it's a complex context. In contrast, science and logic solves complicated problems, such as rocket science, in trivial contexts. When you do rocket science, you basically computing an orbit to Mars or whatever, but you're doing it in vacuum with no friction, etc. So it's a very simple problem. A lot of physics problems, etc., are like that. And we can plot that. We can plot basically problem complexity against the context complexity. And over here in the corner, we have what's called the absurd region. This is complex problems in complex environments. We cannot do anything about those. They're too outside of our reach. If we stay close to the axis, we can get something done. So over here, we have intuitive understanding, and over here, we have logical reasoning. Okay? Rocket science sits over here, and understanding language sits over there. Notice that it's outside of the reach of what you can do with these reason-based methods. Pool balls sit in the corner here. You can either view pool balls in the scientific way as collision of elastic spherical objects under conservation of momentum, or you can view it holistically as spending a couple of years and learning how to shoot pool and get an intuitive feel for how pool balls work. That's understanding. So in the center here, either one may work. Over here, reasoning outperforms understanding, and over here, understanding outperforms reasoning. Pick the right tool, depending on your problem. Okay, that was the main part. I have other conclusions at the end. I need to talk a little bit about reductionism and holism. This is epistemology 101. Epistemology is the science or the discipline that discusses what we know, how we can know it, what we can learn, etc. How we learn. I sometimes talk about reductionists versus holists or people, and it's not to disparage anyone one way or the other, but basically, if you're a person who prefers reductionist methods, reductionist solutions, you will gravitate towards professions where such problems exist, such as programming or science. On the other hand, if you have more a holistic bent, you look at the big picture, then you're likely to gravitate to other professions. Consider scientists, engineers, surgeons as reductionists. Consider authors, teachers, nurses, and architects as holists. A nurse deals with the entire patient, whereas a surgeon focuses on the problem. Architects have to know what it's like to live in a house before it's built. They have to think about everything that matters. And authors and teachers have to be able to explain large contexts to people piecemeal, so they have to understand this large context. Zen and the Art of Motorcycle Maintenance by Robert Pirsig is basically the best layperson's introduction to reductionism and holism. Zen is the most holistic thing a lot of people know, and motorcycle maintenance is a very typical reductionist activity. And the book is a travelogue across part of the United States, but it's also a travelogue where the protagonist goes from a very solid reductionist point of view to one that encompasses both the reductionist and holistic viewpoints. Notice that Pirsig uses a slight euphemism. He calls the reductionist thing, he calls that the classical, and the holistic viewpoint, he calls that romantic. Read that book. It basically discusses how deep is the chasm in our society between the two people, between the two kinds of people, or between the two viewpoints. Reductionism. If you look it up in the dictionary, you will find a bunch of definitions. Like ontological reduction, epistemic, it's all physics, theory reduction, one theory of everything, methodological reduction, the whole is equal to the sum of its parts. That's the battle cry of the reductionist. Context reduction is my favorite. Ignore the irrelevant. In a closed system, all else being equal, you recognize those from physics textbooks. They are basically trying to make a trivial context that you can operate on with your slide rule and calculator. But all of these definitions of reductionism have one thing in common. They seek simple models of our complex reality. So we could look at that and we can say reductionism is exactly the use of models. And if that's the only thing you remember from this talk, I've done something good. Reductionism is exactly the use of models. You simplify reality and to a model that you compute on that. What are models? Scientific models are obvious choice, but we make naive models in our heads occasionally, and we use them and we may share them, but we don't subject them to peer review. Hypotheses are half-baked models. Theories, equation formulas are small, succinct models. F equals ma, Newton's second equation is my favorite example of a model because it's so easy to explain. Computer programs are big models. Programming is the most reductionist profession on the planet. A programmer sits all day and makes models of the world and puts them into the computer. And this is kind of where we went wrong with AI, because AI came from the computer science departments in this world. So all the hardest reductionists on the planet were trying to figure out how to make intelligent machines, ignoring everything we learned from psychology and epistemology and other things over hundreds of years. Okay? Here's a bunch of numbers from an experiment or so. And we can plot those in a graph if we want. And then, as good reductionists, we can basically fit the curve to those using regression of some kind. This is not a model, this is not a model, this is a model. Can you see the difference? Models are understandable, elegant, and compact. Once you have that thing, you can throw away all your data. You can carry that around, that's all you need to carry. And you can do other things that you can't do with just this. You can extrapolate, for instance, to numbers you haven't seen before. You can interpolate between the numbers and so on, if it's a linear function, a continuous function. But what if the data looks like this? It's all over the place. Sometimes making models may be impossible. So there's limits to reductionism. We have to recognize that. So now let's look at some problem-solving strategies for both kinds. I have to talk about reduction. Reduction is basically, well, it's kind of a synonym to abstraction, to higher level concepts. But abstraction is a mathematical concept. It basically sounds like it's perfect. When we make an abstraction, it's like, yes, we got it's perfect, it's right there. But when we are doing reduction, we recognize, when I use the word reduction, I'm recognizing that in the abstraction that we make, we're discarding stuff. We're discarding that which is estimated to be irrelevant. Now, if our estimate is wrong, we're making a reduction error, and our model may be incorrect, but basically this is what we do. We discard that which is irrelevant and make a smaller model. This is the first step in all story problems. If you ever solve a story problem, I know you all have, when you're going from the rich world, explaining the story problem, to a formula, how did you do that? You don't actually, there is no pathway, no algorithmic way to go from the story problem to the formula, to the equation that you finally plug in your numbers in. This is the process of reduction. It requires that you understand the world enough to be able to put up the model on your own. So reductionist problem solving looks like this. There is always a context or environment. And you have a thorny problem in that context. It has tendrils all over the place of the context. You want to solve that one, you can't, it's too complicated. So what you do is you make a model, you make a reduction to a model. Some simple equation maybe, or something more complicated, maybe you write a computer program. But at any rate, you can solve that model using maybe a pocket calculator, a flight rule, or whatever. And then you get an answer, and you can take that answer, you can apply it back into reality. Both of these processes, both the reduction and the application, requires an intelligent agent. It requires understanding of the problem domain. It requires understanding. This is the reason we cannot use, another reason we cannot use logic for making an AI, because as we're building a machine to understand stuff, we don't yet have the ability to build models. This is a chicken and egg problem. Fortunately, there's a way around that. Holistic problem solving. We are doing it without models. How do we do it? We do it, solve it directly in the context or environment. And I should mention right away that this is typically a bit more expensive than using a model. It can be very much more expensive. But our computers are now getting big enough that we actually can afford to do it this way. Big data is largely about how to solve problems without creating models. So since we're not using models, we call these methods that we use, we call them model-free methods. Let's take an example of from genomics, which uses quite a lot of model-free methods. Suppose you have the DNA sequence, or just even the S&P data for some person, maybe you got from the spit or something. And you want to make an estimate of what are the chances this person will get, say, lung cancer. Well, if you want to use models for this, we have a long way to go. First, we have to decide which part of the base pairs, which base pairs are important and which are not part of any gene. So we model the genes in the base pairs, from the base pairs. But there's basically some of them are not part of any gene, they're inert DNA, junk DNA. And then we model the transcription from that into proteins, and those proteins give us the cell function, and errors in proteins and cell function give us pathology, and then the pathology gives us observed symptoms, and those observed symptoms can lead to a diagnosis. We don't know how to build half of these boxes. Okay? Most of this stuff is still out of the reach of science. This is a very iffy thing to do. Can we do it holistically? Yes, we can. We take the same data, and then we interview people. We take data from 1 million people, and then we interview the people, and we get basically groups of diseases. These people have lung cancer, they have lung cancer in their family, etc. And then we can make a simple correlation between the base pairs in the DNA and the group of people who have lung cancer. And this is exactly what 23andMe does. It's one of the things they do, the other things too. But it basically short circuits all of these models that we didn't know how to make. Okay? Holism is exactly the avoidance of models. Reduction uses models, holism doesn't. Other people with other definitions of holism, this is what I use, this comes from epistemology. So, depending on which flavor of AGI we want to build, reductionist AI research, they attempt to reduce the rich world to simple models which can then be programmed into computers, but this is exactly just regular programming. Any sufficiently reductionist AI is indistinguishable from programming. Holistic AGI research uses model-free methods to create software capable of automated reduction. Again, it's the machine that has to do the reduction, not the programmer. Okay? So I have two summary slides, and this is where the controversial stuff is. I don't know if I have time for questions now, but if you want to corner me later, please use these numbers when you want to debate these points. So reasoning requires models. Model use requires reduction. Reduction requires salience, which is knowing what matters and what doesn't. Salience requires understanding of the problem domain. Understanding requires model-free methods. That's the way we implement, and I believe that's the way the brain implements them. Understanding takes 99.9% plus of brain activity, and I believe we get to understanding in 10,000 lines of code. Okay, slide 2. These are letter. Singularity requires recursive self-improvement. Recursive self-improvement requires an infallible AGI. Infallible AGI requires that we use logic, because otherwise it's not infallible. You can't use statistics, for instance. Logic-based AGI requires a total world model, because if we have a border, an edge to our world model, then we will make mistakes at the edge. So we have to actually cover the whole world if we want to have a completely infallible AGI. Total world models. Well, there's something called the frame problem, which was identified in the 60s by John McCarthy and Pat Hayes. It says the world changes behind your back, so your models are going to be obsolete. How can you fix that? We have a static world, which we don't, or if you have some kind of omniscience, which we don't, or if you have an infinite computation power, like in computronium scenarios, then you could conceivably fix it, but you would be modeling every water molecule in the ocean. So infallible AGIs are therefore impossible. It's therefore impossible. And, getting back to unfriendly AI, if those AGIs are fallible, then they are not invincible. We can pull the plug on them. My recommendations: reductionist logic-based, omniscient, infallible, superhuman, unfriendly, godlike AGI is impossible. Instead, build understanding machines that make many mistakes and learn from them, jump to conclusions on scant evidence, and are capable of automated reduction using only model-free methods, holistic methods. Okay, I don't know if we have time for questions now. I can take a couple. Yes, over there.
I have a question about assessing probability. You talked earlier about living in a world with ambiguous evidence, and we all experience that. I mean, I'm receiving information from you right now, and I'm assessing my ignorance, and I'm assessing how much you know, and I don't have a mathematical answer for that. There is one. I don't know what it is. I don't have time to work it out. But can't you make a program that can assess data? It seems like IBM's Watson has been able to do that. It gives a confidence number with every answer that it gives. So could you talk a little bit about whether that's intuition or whether that's reasoning that IBM's Watson is doing? And what I'm doing right now is I assess your claims.
So the question was about how confident can we be in our estimates, and whether you can look at probability-based system as an alternative. You also asked about IBM Watson. I have been using IBM Watson technology for 7 months. There is actually an open source project called Apache UIMA, Unstructured Information Management Architecture, that is what IBM used in the Watson that was beating the Jeopardy champions. But that stuff is all reductionist. It's all models of language and so on, and ontologies and things like that, the usual stuff that you find in reductionist artificial intelligence. It is symbolic, it is not subsymbolic. And as to with estimating probabilities, this is what they do in Bayesian systems and so on. Bayesian and models are still models. So it doesn't make it less infallible, it doesn't make it more infallible just because you are recognizing that there are percentages and so on, you still can't make a correct guess. Now, humans are better than statistics because the Bayesian people, they are still working on models. They're still simplifying the world into small, simple things like your estimate of an equation, of basically estimating a small fraction of it. But humans don't do that. We don't use statistics. What we do is, well, in general, holists, when they are faced with a difficult problem, they take a step back and try to find a larger context. Reductionists, when they're in trouble, they find a smaller context or subdivide the problem. Holists, when faced with a complicated problem, they try to find a larger context that can then constrain what the interpretation is, what it is. They can disambiguate whatever is going on. Answer your question? Okay.
Thank you. Perhaps I did not understand all the aspects, and I need a little bit more technical figure, but I have two questions. So one is that my impression when you talk about model-free intelligence, or model-free methods, in fact there is a model, but you just you don't program the model is created by the computer itself. So it's not exactly model-free, it's just a flexible model that there is no owner of the model other than the computer. And the second question is, I have an impression of the research program that you have is very similar to the very early attempt to create artificial intelligence for neural networks. What's the difference?
So take the neural networks first. Yes, there are multiple different kinds of neural networks, and some are more reductionist than others. If we look at the early perceptron models that were trained using backward propagation, etc., they are kind of on the borderline between reductionist and holistic. If you go to more modern things such as connectome algorithms or what was discussed in the 1984 book of parallel distributed processing by Rumnard and McClellan, and if you look at impulse-based brain models, those can be made more holistic. But it is possible to pick neural networks and still mess it up and go down the reductionist road. What was the first question about?
The first question was that there is a model.
Yes. That is a very good observation. And I kind of regret using the term model-free methods. I should possibly call them model constructing methods. But the term model-free methods came from the father of Sir Roger Penrose. His name is Lionel Penrose. In 1935 he wrote a paper about how genomicists how people who work with heredity should forget about these models you're making. You're not making it easier, just let the data speak for itself. And that's basically the battle cry of modern big data, and it should be the battle cry of artificial general intelligence programming. Yes?
Based on your time estimate and my estimate, I know you're fairly confident you can produce that result. How far along are you on that?
So my company, Syntians, has written, I and a few co-researchers, we have written 20 systems over the past 14 years. And some of them have worked really well, some of them worked really poorly, and we basically learning piecemeal about which direction to go and what to try next. And we are getting awfully close to something that works. And one of the indicators that we're getting closer to the answer is that the last 4 or 5 machines have all been smaller than the previous one. So the closer you get to the true answer, the more you understand, the better you can make the model. Yes, that. Scott.
One quick question: where is deep learning in relation to the systems you're talking about?
Yes, deep learning is an up-and-coming or already here kind of methodology, and it is largely holistic in general. It can, like I said, depending on who's doing the deep learning, you can still mess up, you can still have language models that you're trying to improve. If you do it right, deep learning may be on the correct path, but there's no guarantees. Yes?
Doesn't mean that it is safe, because if available human computation is small, even if it is available, we think that it is friendly, available, it will become unfriendly and destroy our small mistakes.
Yeah.
So that's the danger from it. Yes.
Okay, this is the last question. fallible AGIs don't have to be safe. Well, I think what the AGIs are going to basically slowly get better over time. We started with something that only understands language, and we can make them understand more things over time. And they're going to, after a while, look like teenagers. So we already know how to deal with fallible teenagers, and that's basically how we have to deal with our AGIs. Thank you very much.